We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello everyone, this is Vishalkumar, Assistant Professor in Mechanical Engineering Department of SNPITRC, UMRAKH. Today I am going to teach the subject Fundamental of Muscle Design, and the topic is Design of Cotter Joint. So first of all, know about the main components of the Cotter joint. So total 3 components are main in Cotter joint. First one is pivot, second one is socket, and third one is Cotter. You can say this one is a male part, this one is a female part, and this is a joining part. And the pivot, this one is the rod, pivot collar, pivot end, and this one is a slot for the Cotter. At the end of socket, this one is the rod, socket end, socket collar, and this one again slot for the Cotter. This one is the Cotter, and one edge of this Cotter is tapered. So this one is the structural view of the Cotter joint. If we go for the dimension, and P is the load acting on the joint. So this one is the axial load acting on the Cotter joint. D is the diameter of the rod. Here it is. Here it is. D1 is outer diameter of the socket. This one is the D1, outer diameter of the socket. D2 is outer diameter of the pivot, or you can say inside diameter of the socket. D3 is outside diameter of pivot collar. D4 is diameter of socket collar. This one is a T1 as thickness of this pivot collar. A is distance from the end of the slot to end of this pivot. This one is a C, thickness of the socket collar. B is width of the Cotter, and this width is a mean width because this one is a tapered side, so we have to take mean width. T is the thickness of the Cotter, and L is the length of the Cotter. So in design of Cotter joint, step 1 is design of rod. So in design of rod, you can easily say this area is the resisting area under the tension. There is a tensile force, so this is the resisting area. So you can say load is equal to stress into area. Stress is permissible stress, that is sigma T, and area for this circular cross section is pi by 4 d square. So from this equation, we can say P is equal to pi by 4 d square into sigma T. In that, sigma T and P are unknown to us, so we can easily determine D, diameter of rod. Next is design of pivot. In that, we have to determine D2, D3, T1, and A. First of all, tensile failure of pivot. In pivot, this is nothing but the slot for the Cotter, right? This one is the load, direction of the load. So load is equal to stress into area, and area in this case is pi by 4 d2 square. So this area is pi by 4 d2 square. We have to minus this area, and this area is nothing but the d2 into t. So P is equal to pi by 4 d2 square minus d2 into t into allowable stress, that is sigma t. So from this equation, we can determine the value of d2. In some empirical relation, we have A is equal to 0.75 into d, T1 is equal to 0.45 into d, and D3 is equal to 1.5 into d. Next is crushing failure of this pivot. So we all know that crushing stress is equal to load divided by projected area. wherever two components of any machine or any two surface of any component are having surface contact and there is no relative motion between them, then there is a crushing stress. So crushing stress is equal to load divided by projected area, and in this case Cotter is in contact with spigot, and that projected area is T into D2. So P is equal to T into D2 into sigma C, and that we have to check that sigma C is within the permissible limit or not. Next is shear failure of spigot. Again, load direction is in this direction, so this one is the parallel area to line of action of force. So tau is equal to load divided by area, and this area is nothing but the parallel area to the line of action of force. So P is equal to, this one is A and this one is D2. This dimension is D2 and this dimension is A. Why here it is 2? Because this is this area and second area is in backside. So this is 2 into A into D2 into tau. Again, from that we also have A and the value of D2. So we have to check the shear stress value is within permissible limit or not. Step 3 is design of socket, and that we have to calculate D1, D4 and C. And that first case is tensile failure of socket. So again, this one is the load of direction of the force, and this one is the resisting area. So P is equal to resisting area into allowable stress. Allowable stress is sigma T. And what about the resisting area? So this one is the pi by 4 D1 square. We have to subtract this area, and this area. So equation of this area is pi by 4 D1 square. First of all, we have to subtract this area, so minus pi by 4 D2 square. Then this area, that is D1 minus D2 by 2 into T. This area is D1 minus D2 by 2 into T. So finally we got pi by 4 D1 square minus D2 square minus D1 minus D2 into T. So P is equal to pi by 4 D1 square minus D2 square minus D1 minus D2 into sigma T. And we have some empirical relation. D4 is equal to 2.4 into D and C is equal to 0.75 into D. Next is crushing failure of socket. So again, crushing stress is load divided by projected area, and here projected area is D4 minus D2 into T. So P is equal to D4 minus D2 into T into sigma C. Next is shear failure of the socket. Shear failure, so again, line of action of force is in this direction and resisting area is this one. So if we check in that, D4 minus D2 by 2 into C for this area, D4 minus D2 by 2 into C for this area, this one is for this side, and again we have to go for back side. So D4 minus D2 into 2, D4 minus D2 by 2 into C, D4 minus D2 by 2 into C. So finally we got the total area is 2 into D4 minus D2 into C. So P is equal to 2 into D4 minus D2 into C into tau. And this case again we have to check the value of tau is within the permissible limit or not. The last one is design of Cotter. Design of Cotter, we have an empirical relation to find out the thickness of the Cotter. T is equal to 0.31 into D. Again here it is a double shear. This is the line of action of force. First resisting area is this one, second resisting area is this one, right? So total area is B into T into 2. So P is equal to 2 into B into T into sigma T. And next is bending failure of the Cotter. Bending failure B is equal to M by Z. So from that, B is equal to under root of 3P divided by 3 into sigma B to the bracket D2 by 4 plus D4 minus D2 by 6 bracket over. From this also we have the value of B, and from this also we have the value of B. We have to choose higher of the both. So from this procedure, we can easily design the Cotter joint. But numerical is that Design and draw a detailed sketch of quarter joint which is required to withstand a load of 30 kilonewton. So P is given to you in tension and compression. The material used for the quarter joint has following allowable stress values. Allowable stress in tension, that is 50 megapascal. So sigma T is 50 megapascal. Shear stress is equal to 35 megapascal. So tau is equal to 35 megapascal. Trussing stress, that is equal to 90 megapascal. So sigma CR, that is 90 megapascal. So from the above procedure, we can easily solve this equation numerically. Thank you.